Alright, so we've done the very first shape that we looked at, which was the simple linear. Okay, so we said linear, hopefully you've worked out whenever the molecule is in a straight line, okay, and Liam spoke about it being a straight shape, we call that linear. And we can have different scenarios where a molecule was linear. The thing was though, for these two there was only one group of electrons, okay, that we're worried about. Here there's only two groups, and we said there's only two groups, we're going to repel to be 180 anyway. We could actually almost throw in, alright, that this angle from here to here is going to have to be 180 degrees for it to be completely as far apart as possible. We might talk about angles when we get over here. Alright, the next shape, we've actually got two molecules we're going to work on now, which is water. There's our water shape, okay, and here is our sulfur dioxide shape, okay. Now, if I were to ask you to look at water as being the most simple of the two, how many sets of electrons are there around the water? How many sets of electrons?
One.
Four. Two. How many sets? There's four sets actually, okay? So it's got one non-bonding, that's two non-bondings, that's got 1, 2, 3, 4. So it's actually got 4 sets of electrons around the central atom. 2 bonding, 2 non-bonding, okay? Now we spoke about this briefly last week, but if we drew the structure for water like this last week, we said if we apply the idea that these and these repel, there's 4 groups essentially, they are going to repel. So if all these electrons around our central oxygen repel, it can't be linear. It can be linear if we go from that direction, okay, but when we talk about the shapes of molecule, it's where the atoms are in 3-dimensional space, alright? So water would not look like that, okay, if we actually put the shape of the molecule. Hopefully you can see it's linear. Sorry, it's not linear, is it? What is it? Complex. It's a perpendicular. It's a V shape. We call it a V shape, alright? So it's V shape, or some textbooks will call it bent. It's a bent structure, okay? Now, so we don't draw water as a linear arrangement because it's got four sets that I have to account for. So in total, the number of groups that we're talking about, okay, so I'll put a heading over here again, for groups, it's got 4 groups. However, 2 of those are bonding, 2 of those are non-bonding. So that makes the molecule shape to be a V-shaped. So we'll leave that one for the time being. That's the structure for water, and water is a V-shaped molecule. Or you can use the term, it's a bent structure. Sulfur dioxide, same thing. Okay? If we look at the structure of sulfur dioxide, how many groups has that got around its central atom? Just groups, not pairs. Groups. It's got 3. So it's got it. Alright? So it's got a group, change colour again. So the group is this whole pair here, that's one group. Okay? It's got a double bond here, that is a second group, and it's got a double bond there, there's third group. There's 3 areas that's electron rich around the sulfur dioxide molecule. Now, 3 of them. So strictly speaking then, if I were to draw the structure like this, okay, that's what we're actually looking at for a sulfur dioxide molecule. The difference is it hasn't got any electrons, sorry, it hasn't got any atom there, but it has got a spare pair. So in reality, sulfur dioxide looks a bit like this, okay? That's the original structure for sulfur dioxide, okay? However, there's no atom sitting up there, but there is, if I take that away, that little thing there means there's still a pair of electrons. So this is V-shaped now. This is V-shaped as well. 3 sets or 3 groups of electrons, 3 groups of electrons. Okay. However, I haven't shown you the non-bonding electrons here, except in the structure here, the sulfur dioxide. Alright, so they're both V-shaped, but there is a subtle difference between the two. One's got 3 sets, one's got 4, okay, that we'll come back to in a minute. So the two shapes, so far linear and V-shaped, water and sulfur dioxide, different number of groups but the same principle applies. Mitch?
Is the pairs just how many bonds can we do?
If I said how many pairs, there's 1, 2, 3, 4, 5. Each bond is a, yeah. But I'm talking now about just groups. We just chuck them all together because in the double bond, all the electrons have to be between the two atoms. So we just say that that's a group of electrons there. All right. I sometimes might use the word pair, okay, but I should be using the word groups. It's the groups that have to be there, so if they're going to be there, they're going to repel, okay, to be in a V shape. But I've got to remember, there's also electrons up here, all right? Okay, that's the V-shaped scenario. We'll leave it there.